First session of the chapter Solid State. So in this session we are going to first talk about defects in crystal systems. So what happens is that in any crystal there is supposed to be a regular arrangement of the constituent particles, but if there is any imperfection, that means any departure from the regular arrangement, that is called a defect. Now defects are primarily of two types: stoichiometric and non-stoichiometric. These are the two primary types of defects. Now stoichiometric defects, they can be classified as: first is vacancy defect, so if any constituent particle is missing from its lattice position, that is known as vacancy defect. Second is interstitial defect. Suppose some constituent particles occupy the interstices. Suppose there is any constituent particle in the interstitial or the void spaces, that is called interstitial defect. The third one is known as Schottky defect. In Schottky defect, what happens is equal number of cations and anions are missing from their lattice positions. So that is known as Schottky defect. So say for example in this particular diagram you can see that for every anion missing there is a cation which is missing. Now the thing is that vacancy and interstitial defects, they are usually found in case of non-ionic solids. So these two are mainly found in case of non-ionic solids, and Schottky defect is usually found in case of ionic solids. So what happens is that in case of vacancy defect, the electrical neutrality may or may not be maintained, but in Schottky defect electrical neutrality will always be maintained. Another thing is that the density in case of vacancy defect, the density decreases Why? Because there are some missing ions, and in case of interstitial defect, the density increases because the constituent particles are in the voids. In case of Schottky defect, also the density increases. The density decreases because there are missing ions from their lattice positions. Then the next one is called Frenkel defect. Now in Frenkel defect, what happens? There might be a missing cation. So the missing cation may occupy a void position. So you can see that this also happens in case of ionic solids. But here the cation must be significantly smaller than the anion. So the Schottky defect is usually found in those in which the cation anion are of similar size, like NaCl, KCl, KBr, CSCl and AgBr. So Schottky defect is usually found in these where the cation anion are of similar size, whereas Frenkel defect is generally found in case of zinc sulfide, silver chloride, silver bromide and silver iodide. So Frenkel defect is generally found in case of those solids in which the cation is significantly smaller than the anion. Frenkel defect does not have any effect on the density. So unlike Schottky defect where density decreases, in Frenkel defect there is absolutely no change in the density. Another thing you will notice that AgBr seems to be a compound capable of showing both Schottky and Frenkel defect. So you can say it is like a borderline case where cation anion are not exactly similar, but in fact the anion is bigger than the cation. So these are the 4 types of stoichiometric defects. Now we come to non-stoichiometric defects. Now non-stoichiometric defects are again of a few types. The first one is called metal excess defect. Due to interstitial cations. So suppose this is the crystalline structure. So let us say that a cation is in the interstitial position and an electron is somewhere else in another interstitial position. So this is called metal excess defect due to interstitial cations. Now in what situations does this happen? If you consider zinc oxide, then after heating, it releases 2 electrons. So zinc oxide is basically white in color. If you heat it, it releases 2 electrons. Oxygen, O2 escapes as oxygen gas, and you are left with Zn2 plus cation. So some interstitial position you will find this Zn2 plus cation, and in some other interstitial position you will find these electrons. So what will happen is that there will be an excess of zinc cation because oxygen gas has escaped. So the molecular formula of zinc oxide will now become something like Zn1 plus XO. Another thing is that these electrons which are in the interstitial positions, due to these electrons, now the substance is yellow in color. So the color now becomes yellow. Why? Because these electrons are capable of taking energy from visible light, absorbing certain wavelengths from visible light, and the transmitted color appears to be yellow. That's why we say that zinc oxide is yellow when hot and white when cold. The second one is called metal excess defect due to anion vacancies you will notice that the structure which I have drawn, that there is one electron in a crystal position instead of anion. So let us look at one example of this. Suppose, let us say that NaCl crystal is heated in presence of sodium vapor. Now the sodium is converted to Na plus and E minus. Now one Cl leaves its lattice position to combine with Na plus, and the electron comes to take the place of the vacated Cl minus. So this Cl minus comes and combines with Na plus, and the electron comes to take this vacated place. So you will get NaCl on the surface, and this position will now be occupied by this electron. Now this particular location is called F center, and F stands for Farbcenter, which is the German word for color. So this is the location which is known as a color center. Now when visible light falls on this crystal, this electron absorbs certain wavelengths and the transmitted color is yellow. So that is why the crystal has a yellowish appearance, because the electron which comes at the F center is able to absorb some wavelengths and transmit the remaining color, which is yellow. Similarly, instead of NaCl, if you take KCl, then the color is lilac, and if you take LiCl, then the color is pink. Next we come to metal deficiency defect. This particular defect happens in case of cations with multiple valency. Like say for example, this is the structure of FeS. So in the structure of FeS, suppose 3 Fe2 plus ions leave their lattice positions. Suppose 3 Fe2 plus ions leave their lattice positions, and out of the 3, 2 are occupied by Fe3 plus, so that gives a metal deficiency at this particular lattice position. So metal deficiency defect is found in those metals which are capable of multiple valency, like iron, copper, etc. Next non-stoichiometric defect is impurity defect. Suppose you have NaCl crystal and it is doped with an impurity SrCl2, then what will happen is that for two Na plus ions which leave their lattice positions, one will be occupied by Sr2 plus and the other will have a vacancy. So this is known as impurity defect, and it is called an impurity defect because the original crystal was NaCl and we have added an external agent like SrCl2 to it. That's why it is called impurity defect, and there is a vacancy at this cationic side. So that completes the defects of crystal systems, and it also brings us to an end of the first session of the chapter solid state.